Hi everybody! Today we are going to talk about the confidence intervals. Let's remember what they are about. Sometimes we have just samples that we want to analyze what is happening not with the sample itself, but with the population from which the sample is taken. That is, we just have information about what is happening with a little part of the population, but probably we want to extrapolate that into the whole population. When doing that, it is not possible to have an exact value, but thanks to the confidence intervals, we can approximate the real parameters of a population. What we're going to see today are some examples of how to apply the formulas of confidence intervals. For that, let's remember that we have divided this on three parts: large samples, small samples, and we're also going to see the special case for a confidence interval for the variance. The first thing that we need to see is that a large sample is any sample with more than 30 elements or just 30 elements. Less than that, it is considered a small sample, and we're going to see that the formula changes slightly. However, for the variance, we can use it as long as we have a population that we consider that has a normal distribution. Let's look carefully at the formulas. What we can see is that with the large samples, we're going to be able to analyze what's happening with the mean, with the difference of means, the proportion, and the difference of proportions. Look that every formula has pretty much the same syntax. At the beginning, what we have is an estimator. This estimator is what you saw in the first partial of this course, because we just have the mean, the sample mean that we obtain from a sample, a difference of sample means, or just a proportion. How do we find the proportion? It's just a frequency. How many elements we're observing that has the characteristic that we are looking for over the total number of elements that we have just sampled, or a difference of proportions, just as in the case before. What you need to see is that after that estimator, then we're adding and subtracting certain element. That addition or subtraction is telling us that the confidence interval is going to be symmetric. That is, this estimator, what we obtain from the sample, is going to be located just at the middle, and then we're going to add and subtract the same quantity in such a way that our confidence interval is telling us that we can be mistaken a little bit over that value that we have, or a little bit behind that value that we have observed from the sample. This element that we have in here is called the estimation error. The estimation error, here it is. This is called the estimation error. The estimation error means how large we can be mistaken on trying to find what is the parameter by just observing a sample. What I need you to notice is that this estimation error has two parts. The first part is what we call the confidence level. The confidence level is just telling us how large or small our confidence level is going to be. As larger is this C, we're going to see that the confidence level is larger and the confidence interval is larger. It means that there are more probabilities of really finding what is going to be the real parameter. However, it is also related with this element that we can see in here. This is called the standard error. The standard error is nothing but the standard deviation from observing what's happening with your sample divided by the square root of n. The reason of this division is, if you have more data in your sample, you're going to see that your confidence level is even better. And the reason is that your estimation error decreases because this denominator is increasing as your sample is increasing. The goal in every confidence level or every confidence interval is to have the best possible approximation, and that requires to this estimation error to be as smaller as possible. So we're going to see that in every of these formulas we have these two elements. We always have a confidence level, in this case represented by this C. We're going to see on the examples how this C is just referring to our standard normal distribution. But this standard error is changing formula by formula. It does because for each parameter that we want to estimate, the formula is different, even that the logic of each formula is the same. For example, in the difference of means, the estimator is going to be the difference of sample means. We have the same confidence level, and this standard error is going to change into this little function. The same happens with P for estimating a proportion or a probability. What we will see is that P hat is going to be our estimator, the same confidence level, and again we have the standard error calculated just as in a binomial distribution. The same happens on the difference of proportions. An estimator, the confidence level, and finally the standard error with this formula that we have here and you also have on your formula lists. If we move slightly to the small samples, we're just going to analyze one case, and it is the case of calculating the mu. I need you to notice that this formula and this formula are almost the same. We have the same estimator, we have almost the same standard error. The only thing that changes is that here we're using sigma, that is the known standard deviation of the population if available. But here we're going to suppose that because we have a small sample, it is impossible to really know what is happening with the real standard deviation. So where this is coming from? From the sample, the same sample from which you are calculating X bar. However, look carefully at this. The confidence level changes. Now the confidence level is not using the standard normal distribution. It is using the t-student distribution. It's just a little change that we will see that affects the confidence level, but is going to improve our estimation when having a small sample. Finally, the last confidence interval that we're going to see examples of is the one of the variance. In this variance, I need you to notice that this is slightly different than what we have seen before. We're looking that we do not have a plus and minus. It is still symmetrical, but not in the same way as before. We're going to notice that now this sigma square is going to be what we want to estimate. In order to do that, we already know that this parameter, the estimator of the parameter, is the sample variance, denoted by S squared. Look carefully how this S squared is in here and also at the final part of the confidence interval. In both cases, it is multiplied by n minus 1. This n minus 1 is also known as V, the degrees of freedom. V is nothing but the parameter of a particular distribution that we're using for this confidence interval, the chi-square distribution. The chi-square distribution is a positive distribution that has a behavior of something as this. What we're going to notice is, because of this behavior, we cannot have a positive and a negative part as in the previous confidence intervals. What we need to do is to consider two values. A large value that is going to be located somewhere over here, and a small value that is going to be considered somewhere over here. These values are the ones that will give us the confidence interval for the variance, and the procedure is slightly different. That's the reason we're looking at this example at the end of this video. So, if you agree, let's start with the exercises about large samples, and then we continue with the rest of them. In this exercise, I'm going to ask you to please follow me by using PYQRS as long as your formula list to understand the concepts that we will be seeing. The exercise says, a hospital wants to analyze the average number of days required for a certain treatment. A random sample of 500 patients produced a mean of 5.4 and standard deviation of 3.1 days. Find a 95% confidence interval for the mean length of stay. The first thing that we need to do is to look at the exercise and understand what is the parameter that we want to analyze. We need to see that they're asking us for the mean length of stay because it is a mean. We know that what we will be using is the formula for mu, the confidence interval for mu. That is x bar plus minus the confidence level times the standard error. What we're going to do now is to analyze from the context what are the values that we require. X bar is given explicitly on the text. It says that it is a mean of 5.4. The standard deviation is also given explicitly on the text. It says that it's a standard deviation of 3.1. Here we can ask ourselves, and what are we using the formula for a large sample and not the one of the small samples? The reason is at the beginning of the text. It is telling us that a random sample of 500 patients. These 500 patients is in the sample size. Because 500 is larger or equal than 30, we can say that we can use a large sample to analyze the confidence interval. We almost have all the information. If you just notice, we're just missing what's happening with the confidence level. They tell us that the confidence level is 95%. What we're going to do then is to analyze it as follows. If the confidence level is 95%, it is said that 1 minus alpha is 95%. We're going to notice in the formula that that is not 1 minus alpha what is required, but alpha halves. So we just need to find what is alpha halves. From here, it is simple to see that alpha then is going to be a 5%. Hence, alpha halves must be 2.5%. In order to find what means C of alpha halves, we need to use the standard normal distribution. In this standard normal distribution, it is important to notice that what we want to find is that this probability of alpha halves is located at each of the tails of the distribution. In other words, I need to find a value in here in such a way that the probability on this tail is 2.5% and another value on the other side in such a way that this probability is also 2.5%. It is important to remember that the standard normal distribution is symmetrical and also it is centered at 0. That means that the value that I find in here and the value that I will find in here are going to be the same in magnitude but with opposite signs. That is helping us to in fact find a symmetrical confidence interval as we said before. If you do this on your PYQRS, you are going to notice that this value is minus 1.96, while this one is the positive part, 1.96. Please try it at home. With these values, we're going to notice that the only thing we need to do now is to substitute the values into the formula. Let's do it. When substituting this on the formula, we're going to notice that X bar was 5.4 plus minus. This C of alpha halves is the one that we just calculated. The minus and the positive sign are this minus and positive sign. So you need to add and subtract 1.96. Sigma is not given on the text. However, we already know that the best estimator for the standard deviation of the population is the standard deviation of the mean. So instead of using sigma, we're going to use S, 3.1. Finally, we're going to divide it by the square root of the sample size. In this case 500, and that is the reason why we're using a large sample. Let's put this operation in the calculator and let's find out what the answer is. We find in the calculator that the answer of these two operations is 5.13 and 5.67. Please try it yourselves to see that the results are the same. But what does these results mean? What we are trying to estimate is the average length or the mean length of stay, but not just for the sample but for all the population, that is, all the patients that are receiving this treatment. The procedure of the confidence interval is not going to give us a simple answer or a single result, but it is giving us the complete interval. It means we don't really know what the real mean is, but we are 90% sure that the average is located between 5.13 and 5.67. We know that it is not 5.4 as we just saw on the sample, but it may vary a little bit. That is the estimation error. But that varying part is not that much. We can see that we are not changing this 5.4 too much, but just a little bit by decreasing it to 5.13 and increasing it to 5.67. So this can give us a much better estimation of what can happen not with the sample, but with the whole population. Let's do another exercise, in this case of a difference of means. In this second exercise, we're going to analyze a difference of means. It says, an experiment to compare the days required to double the size of a bacterial population under different temperatures gave the following results. These ones that we have in here. Look carefully how everything is for a sample. In the first case, a sample of 34 elements. On the second one, a sample of 41. The sizes are different. X bar is the average time required for each of the cases, and S is going to be the standard deviation. They're asking us a 99% confidence interval for the difference of means. Again, it is easy to see that we're using 34 and 41. In both cases, the quantities on the samples are larger than 30. Because of that, we can say that it's a large sample confidence interval, and we're going to use this formula that we have in here. Please identify it in your formula list to be aware what we are using. On this confidence interval, we need to see that the elements that we require are almost everything given on the text. We have the different means, we have the different standard deviations, but we require the variances. We have the different quantities n, as we can see in here, and the only thing that we are lacking is the confidence level. However, we already have what's happening with alpha. Please just notice that 1 minus alpha, in this case, is 99%. It means that alpha is going to be 1%. But again, we require alpha halves. Alpha halves then is going to be 0.5%. The procedure is similar. Please follow me on PYQRS to verify the results. We're going to find a boundary on this part and a boundary on this other part. Remember that the boundaries are symmetrical. The probability that we're looking on the left tail is going to be this 0.5%. In PYQRS, remember that we cannot write the percent, so this must be set as 0.005. The same is going to happen on this other tail in which we're going to have the other 0.5%, or what is the same, 0.005. When doing that, you're going to see that the values corresponding to the C of halves are minus 2.576, and in the other case, the positive part, 2.576. Please verify it in PYQRS. We now have all the information required for solving the exercise. Again, the only thing we're doing is being aware that a difference of means is being requested of large samples, and it's because of that that we can use this particular formula. I substitute the values, that is 24.8 minus 21.3 plus minus 2.576 times the square root of 7.1 to the square divided by 34 plus 8.1 to the square divided by 41. I just need you to notice that in this formula, we're taking just the values given on the text and using them for calculating the confidence interval. From here, the only thing we need to do is to put this on the calculator. Let's do it, and let's find what the result is. We're going to notice that the result in this case goes from minus 1.022 to 8.022. Again, the original difference that was about 24 minus 21, about 3, is going to be located in the center. But what is important from here? Remember that what we want to analyze in this case is the difference of means. If the mean of the first population is the same as the mean as the second population, then this difference should be 0. That means, if we're able to find that that 0 is inside of this confidence interval, then the logical result is that statistically both populations have exactly the same mean. And the reason of that is we don't really know what is the true parameter, but we are 99% sure that it is located between these boundaries. It is easy to see that inside of this interval is in fact that 0. And because of that, what we can conclude is, with this information, at a 99% confidence interval, we can say that both populations have exactly the same mean. Here you may argue, but there is still a chance of having a difference of 8 or a difference of minus 1, in which either cases we're going to have a difference of both. But it's not what we are trying to say, what is the real value. What we just want to see is if the 0, a possible result with the same probability as anything else, is inside of the interval. Hence, the conclusion is that both populations are the same. What will happen if the 0 was outside of the confidence interval? A positive, always positive confidence interval is going to tell us that the first population is larger because the result of the subtraction is positive. If the 0 is outside of the confidence interval in such a way that this is always negative, then we're going to say that the second population is larger because the result of the subtraction is negative. Here, a possible question is, and which one do we consider as the first population and then the second population? Doing that is not really important. If you just change the order of the operations, the only thing that is going to change is the sign. It's going to result into a positive 1 and a negative 8. You can try it to see how we can do it with different possible allocations of the populations. At the end, understanding the meaning of the confidence interval is really simple when looking at a 0 in this case, because it is a difference. Again, if the 0 is inside of the confidence interval, then both populations are statistically have the same mean. If the confidence interval is either completely positive or completely negative, It means that there is a difference on either way of the exercise. Let's go to the next exercise about a proportion. In this exercise, the text says, the results of a survey applied to 800 randomly chosen adults indicated that 45% think that action movies are getting better in the last years. Find a 90% confidence interval for this proportion. Here it is easy to see that they are analyzing 800 people, and because of that 800, we can say that it's a large sample. We can also see that they're asking us for a 90% confidence interval for this proportion. We can also see that they are referring to a sample proportion obtained already in the text. So everything indicates that the confidence interval that we need to use is the one for a proportion. Please look at this formula in your formula list to be aware where it is located. Most of this information is already given. However, we are missing, again, C of alpha house, but also Q hat. We're going to see that Q hat is just the complement of the probability or proportion that we want to analyze. In this case, 1 minus P hat. To calculate what's happening with C of alpha house, we just follow the same procedure as before. It is given that the confidence level is 90%. That is, 1 minus alpha is 90%. Alpha then is just the complement 10%, in such a way that 90% plus 10% is 100%. Then we're just going to say that alpha halves corresponds to 5%. When looking in PYQRS, and please check it out in your computers to see that we have the same results. When looking at this tail with a 5% probability, or what is the same, a 0.05, and in the other tail, the other 5% probability, or again, the 0.05 that you need to use on PYQRS, we're going to notice that the value that we have on the negative part corresponds to minus 1.645. On the positive part, 1.645. Please try it at home to see that we have the same results. With this, the only thing we need to do is to substitute values in our formula. Let's do it. P hat is given, it's 45%. We cannot write it as 45% itself. Let's remember that this is just a representation. So we need to use 0.45. If we try to use this formula with a 45, not an 0.45, we're going to have a terrible result. 0.45 plus minus, and this C is the one that we calculated on PYQRS, 1.645. Then in the square root, please just notice that P hat is the one that was given, again, 0.45. Well, the complement in this case, we can just find it out by subtracting 1 minus 0.45, that gives us 55%, 0.55. Then we just need to divide it over n, the sample size, that is said to be 800 people. Let's put this on the calculator to find the result. The result in this case is nothing but 0.42 to 0.48. What we can notice in this confidence interval is that now it is giving us the possible proportions in the population of adults, not about just the 800 people. And what we can say is that between 42 and 48 is going to be the average proportion if we start asking all the people in the population, or not the average proportion, so sorry, but the proportion in the population. On this context, if they are thinking that the action movies are getting better, or in the other way, they are getting worse, we can think that if the 50%, that is half, is located in the interval, it will mean that, yet the action movies are pretty much the same. Half of the people think that they are better, the other half think that they are worse. What is happening on this case? The 50% is outside of the interval. That is, the proportion of people thinking that the movies are getting better is smaller than 50%. Statistically, we can say that there are more people thinking that the movies are not getting better, and we can infer that they believe that the movies are getting worse. Just for you to think about it before going to the cinema. Let's go to the next exercise, in this case about the difference of proportions. In this exercise, we are going to analyze how to solve a confidence interval for a difference of proportions. The text says, for the comparison of the defective rates of two machines, 100 items produced in each machine were tested. Machine A yielded 18 defectives, machine B just 12. Find a 98% confidence interval for the difference of defective rates. Here we need to see that they are not really telling us that it's a difference of proportions, but they are telling us that it's a difference of defective rates, and the rate is nothing but a proportion. So we already know that we need to work with difference of proportions. Look carefully at how many items we are analyzing from each machine, 100. It means that it's a large sample, so it's pretty obvious that we need to use this confidence interval formula. Please, look at it on your formula list to check out where it is located at. From here, what we need to do is to analyze from the text where is the information given. Unfortunately, they are not giving us what is happening with the proportions. And by the way, something is wrong in the formula. Can you check out what is missing? That's correct. We are missing the confidence level. Here, we need to include plus and minus C of alpha halves. So again, if we just try to analyze what's happening with the information, we can be aware that the proportion is not given. They're just telling us that 100 items are produced and 18 and 12 defectives are found. It means that probably there is a possible way to find out what is happening with P1 hat, or let me call it PA and PB hat. In both cases, we're analyzing 100 items. That's the denominator, just as in probability theory we saw. In the numerator, it's the amount of items that are in fact defective, because that's what we want to find out. In the first case, it is 18, as in the second one, it is just 12. It means that this is going to be a point 18, and this is going to be a point 12. By just looking at these numbers, it is pretty obvious that machine A has more defectives than machine B. But statistically speaking, can we really say that this difference just of the estimators is correct? We need to use the confidence interval. And again, how are we going to notice if both machines have the same defective rates? You are correct. If in the confidence interval we have inside of it a 0, because that will mean that the difference we are subtracting to things that are equal. Let's substitute the values, but first we need to find what's happening with the confidence level. Let's repeat the same procedure as before. It is telling us that it is a 98% confidence interval. It means the confidence level 1 minus alpha is 98%. Hence alpha is 2% and alpha halves is 1%. In PYQRS, and please follow me at home, we need to find in the tails a probability of 1% and a probability of 1%. We're going to notice that the value that gives us on a standard normal distribution a probability of 1% on either tails is going to be minus 2.326 on the left tail, and the positive part 2.326 on the right tail, just as we did before. Now with this data, the only thing we need to do is to substitute it in the formula. We already know that PA in this case, and let's do A minus B. A is going to be 0.18. The probability of B is going to be 0.12. Plus minus. The confidence level results to be 2.326. And then on the square root, we just need to include P hat and Q hat. Let's remember that Q hat is the complement of P hat, that is 1 minus B. So what we're going to use is 0.18 times 0.82. Everything divided by the amount of data analyzed for that machine, 100. This is just for machine A. Plus, I then go to the second machine. I have a probability of 0.12. The complement results to be 0.88. And again, I have another 100 items for machine B. That is 100 items for machine A and 100 items for machine B, just as the problem is telling us. Let's put this into the calculator and let's find what the result is. In this case, the confidence level, or the confidence interval, sorry, is from minus 0.06 to positive 0.18. What we can see is that the confidence level, the confidence interval is huge, but who is inside of that confidence interval? The zero is. It means we can be 98% sure that the effective rates in both machines is pretty much the same. Well, how can we use that information? If we have certain amount of money and we want to use it to improve our machine A or machine B, will it be better to invest it in one or another? Not in this case, because they both have the same effective rates, so we can use the money on either of those and the result is going to be the same. But you need to be aware of the following. This is given with a confidence level of 98. What will happen if we decrease the confidence level? For example, what will happen if instead of 98, we want to use a 90% confidence level? What you need to be aware of is that these tails are going to increase, because now instead of just having 1%, you're going to have 5% and 5%. Then your confidence interval, instead of being this large, is going to be decreased. When decreasing, there is a chance that the zero is going to be on the left part of it, and this is going to be exclusively positive. And if it is positive, it means that in fact A is providing more defectives than B, but we need to test it. Please try it at home and then check what the result is and how it is changing when modifying the confidence level. Let's solve another exercise, in this case about a small sample. Remember that with small samples, we're just analyzing the mean, but let's take special care of what is changing on the following exercise. In this exercise, the text says, a scientist collected 5 data points from observing concentrations in parts per million of a certain alloy in water. These are the data points 21, 19, 10, 5, and 8. Estimate the 90% confidence interval for the average concentration. Here we can see that they're asking us for the average concentration, which means that we're referring to the mean, to mu. But there is an issue because we just have 5 data points. This is certainly less than 30, and then we cannot use a large sample formula. We need to use the small sample confidence interval. The formula is really similar Look carefully how we're still looking at x bar, we're still looking at the standard deviation and the square root of n, but the only thing that changes is that now we're not going to be using a standard normal distribution, but now it is important to use a t-student distribution, or just t-distribution as it is located in PYQRS. When looking at the information, we can see that this is not necessarily given on the text. They are not telling us the averages, they are just telling us the data points. What we need to do is to remember everything that you saw on the first partial. By analyzing these with descriptive statistics, we can find the average x bar by just adding the data points and dividing it by 5, or well, the standard deviation s squared by just adding each of the data points minus the previous average raised to the square, adding everything and dividing it by n minus 1. However, we can also do this in Excel by just using the formulas average and variance, or even standard deviation for a sample. This information that we have in here, and please try it in your Excel, or if you prefer to do it by hand, must give us the following result. X bar is going to be 12.6, while s squared is going to give us a result of 59.3. Please verify it in your own computer, doing this in Excel and checking that we have the same results. Remember that we are here analyzing the variance and not the standard deviation. The standard deviation is just this square root. What we're going to do is to substitute these elements into the formula, but for that, we require the confidence level of t alpha halves. For doing that, we're going to repeat exactly the same procedure as before. We already know that the confidence level 1 minus alpha is 90%, which means that alpha is 10% and then alpha halves is 5%. In this t-student, we're going to try to locate the 5% in here and the other 5% on the right tail. But there is an issue. The t-student is not like the standard normal distribution that has parameters of a mean 0 and a standard deviation of 1. The parameter of the t-student is b, the degrees of freedom. We're going to notice that this b, the degrees of freedom, is nothing but n minus 1. It's the definition of degrees of freedom. You also need to be aware that this n minus 1 is also present on this formula in the one of the variance. It's the degrees of freedom is going to be a value that is located several times on all these inferential statistics. By analyzing n minus 1, and please follow me in your PYQRS, you just need to look for the t-distribution entering a parameter, in this case of 5 minus 1, that is 4. This 5 is the amount of data points that we have on our small sample. We are always subtracting 1 by definition of the degrees of freedom, and that gives us 4 degrees of freedom as the parameter of our t-student. As larger the degrees of freedom, the t-student is going to be more similar to a standard normal distribution. That's the reason why, when we have more than 30 elements, we don't really need to use the t-student. We just go with the standard normal. In this case, again, using the t-student distribution, we're going to notice that we require a 5% on the left tail and a 5% on the right tail. That is, the 90% is on this body of the distribution. When doing such, we're going to notice that the values that you will find on the negative part is going to be 2.13. On the positive part, it's also a symmetrical distribution being a positive 2.13. With this, we have all the information required for substituting in the formula and finding the confidence interval. In this formula, we just need to see that x bar is the value that we just calculated, 12.6. Plus minus, this t of alpha halves is in this case the 2.13. Again, Just remember that the positive part is the one of the right tail, and the negative part is the one of the left tail. It's a symmetrical confidence interval. S is already obtained by this formula, but be aware that S is the standard deviation and this is the variance. If you just calculated the standard deviation using Excel, please use that value. Otherwise, we need to use the square root of 59.3. In the denominator, we're just going to have the square root of n, that is the square root of 5. Let's enter this information into our calculator to see what is the result. After solving this operation with our calculator, we can see that the confidence interval is from 5.27 to 19.94. What we need to see is that in this case, the confidence interval is slightly larger than if we use it with the standard normal distribution. That is happening because we just have 5 data points. Hence, the quality of the information that we have is really small. In order to avoid making a mistake, the T student is going to provide us a much larger confidence interval than the one that we can obtain using a standard normal distribution. Hence, we can see that this interval, even it has a greater estimation error, it still has the 90% confidence level required, and we can be sure that 90% of the times the average of the concentrations in parts per million is going to be between 5.27 and 19.94. Again, it is impossible to know a particular point because this 12.6 is just the average that we found on the sample, but we are trying to estimate not the sample but the whole population. Let's go to the last exercise that is about finding what's happening with the variance. In order to do that, we're going to use this same exercise so we can analyze what is happening with this S squared of 59.3 and how we can use it to analyze or to calculate a confidence intervals for the variance. In this exercise, we're going to use the same base as in the previous one. The same scientist is collecting the same 5 data points. Again, we have a small sample, but please look in your formula list to what's happening in the assumptions of the variance confidence interval. It's not required that we really have a large or a small sample as long as it comes from a normal population. So let's assume that this is from a normal population. We have the same data points 21, 19, 10, 5, and 8 from which we already know that the variance is 59.3. So we're going to use this value of 59.3 to analyze, in this case, a 90% confidence interval for the variance. When analyzing this variance, what you need to notice is that now the formula is going to be different. Please search in your formula list for this expression. Probably this is slightly different in your formula list, but the result, it doesn't matter if it's expressed with inequalities or just in an interval, is going to be this expression. The degrees of freedom n minus 1 multiplied by the sample variance divided by the chi-square, written like this, chi-square of alpha halves, and in the other side, pretty much the same but the chi-square of 1 minus alpha halves. We already have this information. We know that it is 4. 5 minus 1. We already have S squared. We calculated before using Excel with 59.3 or just with the formulas of the previous exercise. The only thing that now we are missing are these two values, these two expressions taken from the chi-square distribution, and I'm going to ask you to please use your PYQRS to follow me on the exercise. Using PYQRS, you need to search for the chi-square distribution. It's going to require us for the degrees of freedom, or V. Let's remember that V is always following the same formula. V is n minus 1. So in this case, it is 5 because we have n data minus 1, and we're going to have a 4. The same 4 that we have on this expression in the formula. What we're going to do then is to search, and please be aware that this is an always positive distribution. We have just positive numbers on this x-axis. It means that then what we're going to try to do is to find a probability, let me call it on this kind of left tail, and another probability on the right tail. You're going to notice that when finding a probability of, and again we just do the same procedure, if 1 minus alpha is 90%, alpha is 10%, and alpha halves is 5%. So what we want is a 5% on this tail and a 5% on this other tail. That's the reason why in the formula it says alpha halves and 1 minus alpha halves. Why? Because it is considering this 5% and then this other expression of what's happening. Well, this 5%, so sorry, and then the other probability that is what is left, and the other 5% is on the left tail. When you do this procedure, you're going to find out that there are two values that are arranged. The first one is 0.71. Please check it out in your PYQRS that you have the same result. On the right part, on the right boundary, the value is going to be 9.49. Please again, check that you have the same results in your PYQRS. You need to notice that you will always have a small value and a large value. The small value is the one that we will be considering on the upper boundary. The large value is going to be the one that we consider on the lower boundary. The reason is that we have the same values, but they are being divided by two expressions. If we want this to be a small element, we need to divide it by the large value that we find. If we want this to be the large value or a large element, a large boundary, we need to divide it by the small value. So we're just going to substitute that on this expression. 4, that is the n minus 1, times 59.3, that's already to the square, that's the variance already, divided by this value that in this case is 9.49. This must give us a small boundary, the lower boundary of the confidence interval. On the other part, I use the same, 4 times 59.3. I'm not modifying anything. However, in the denominator, I just use the other value that I just found, 0.71. Please be aware that we're not using t-student anymore. We're not using the standard normal anymore. We're using the chi-square distribution. That's the reason why we have these two elements on the formula. When doing so, we're going to find that in this case, the interval is going to give us from 25 rounded to 334.1. Again, rounded. This is just telling us what is the confidence interval for the variance. In other words, we are 90% sure that the real variance of the population, not just these 5 elements, is located between 25 and 334. What will happen if we are not interested on the variance, but we're interested on the standard deviation? Remember that the standard deviation is the square root of the variance. So the only thing that you will need to do is to take the square root of both. In other words, if what you want to find, this is the confidence interval for the variance. If what you want to find is the confidence interval for the standard deviation, the answer is pretty much the same. Again at 25 and again at 334.1. So what is the difference? We are going to apply a square root. Basically, those are the cases that we are going to see about confidence intervals. As you can see, it's just applying formulas and using correctly the distributions or the probability distributions that you have seen already. What I'm going to ask you then is just to practice. Try these exercises at home and check that we have the same results. Also check on the chapters of the book, everything related with confidence intervals. you will see that applying confidence intervals is really simple and it's really useful. And I hope that it will be particularly useful for your next semesters in the next classes in which you will be using the statistics. Thank you so much for your attention. See you later.